Hi, everyone. So as Daniel said, I'm Oliver. Before I start, I just want to say a massive thank you to all of the organizers of this conference. It's one of the best run conferences I've ever been to, so just massive thanks for them. So today I'm going to talk about mobile digital identity, specifically around mobile. Many parts of this talk are still being actively evolved through industry specs as countries are slowly building out their different implementations. And some of the other bits I've oversimplified just to get through it in about 20-25 minutes. So please do read through any of the industry specs before you start building anything. But hopefully this is a good overview for you. So there's been a lot of talk about decentralization over the last few years. And generally, when we talk about decentralization, often it's sharing responsibility across different servers for things like cryptocurrencies and social media like Blue Sky and Mastodon. But I think the biggest benefits of decentralization are actually relying less and less on centralized servers containing masses of data. And a lot of Apple's privacy features come from actually this approach. So things like biometrics for Face ID and Touch ID never leave your device. Apple Health data is all processed on the device. Sensitive content detection runs on device, and much of Apple Intelligence, as well as the stuff that Avi talked about just now, also just runs on the device, so it's never sent, and you have control of that data. And so decentralization can give a lot of control back to our users and produce a much more privacy-focused world. So where does mobile identity come into this? Well, decentralized identity using mobile devices is gaining traction worldwide. India's Aadhaar system actually already serves over 1 billion people. Estonia's e-residency system allows non-Estonians to access the country's digital services, allowing them to establish and manage EU-based businesses without even setting foot in the country. And the EU's new IDAS regulation requires member states to offer standardized digital wallets that enable citizens to store and share their identity data. Speaking of standards, this talk is based on a variety of industry standards, and though we don't have time to go through too much detail about each of these, individual implementations across different geographies will also slightly differ in the different features that they implement. First, just a tiny little bit about me. I'm Oliver, as Daniel mentioned. I'm a kind of mobile tech lead developer, whatever you want to call it, at Deloitte Digital, focusing specifically on native mobile apps. I've led different teams of developers across the private and public sector clients, and last year I was a finalist at the UK IT Industry Awards for Engineer of the Year. You can find me on these socials if you're interested. I particularly use Blue Sky for the most part. I like the web domain handle thing. I think that's pretty cool, and it kind of ties into the identity piece as well. But yeah. So previously I've worked at a travel company responsible for weight and balance of aircraft on NHS Test and Trace during the COVID pandemic, and more recently with Government Digital Service building identity verification apps for government. Cool. So today we're going to touch a little bit on the core concepts of identity. We'll talk about encryption and signing and cryptography that really is the backing behind that, how that works. We'll talk about a little bit how credentials get issued to a device, and finally how we can use those credentials once they're on their device to verify who we are. So, identity. How does this work? These are probably things you're all familiar with, but we'll just define them a little bit in detail so that we're all on the same page. So first we have the holder of a credential. I'm the rightful holder of my own identity, and I might want to prove that to someone. My identity is made up of different credentials, so you can see some examples of those on the screen. It may be the passport I used to arrive in the country, or the conference pass that I used to get access to the room today. The issuer is the source of my credentials, and this is generally some respected organization who can be trusted to know information about me. So this may be something like Oliver's been selected to speak at iOSKonf, or I've paid for a travel card for the metro, or that I've passed my exams and attained a degree certificate. And finally, there's a verifier, who is the organization or person who wants to know something about me, which may be, have you bought a ticket, or when's your birthday, and are you old enough to come into this bar? And we have this circular relationship between the three of those. So the issuer provides me with my credentials. I can present them to a verifier, and they can verify that data using publicly available data from the issuer. And that publicly available part is really key in this place. And this relationship is really based on trust. And so the issuer trusts that I'm the rightful holder of my credentials, if they shouldn't be giving out my credentials to someone who isn't me. The issuer And then for the holder, I can trust that the person I'm giving my data to is keeping that safe. and the verifier trusts that the issuer wouldn't give credentials to someone that they shouldn't. And so just as with money and debt, a credential is, by definition, something that people trust. Without that, it's just a piece of paper, and it has no value. So, trust. How do we do this with physical documents? Well, with physical documents, we often use complex printing techniques to make sure that we can verify that a document is genuine. We can't really do this in the digital world, because if I create an app with kind of complex UI, even with the world of Swift UI these days, people can replicate that pretty quickly. And so, generally with digital credentials, we use something like cryptography. And this is something you use all the time, whether you realize it or not. Many of you arrived in the country for the conference, you'll have used your e-passport, which has a cryptographically signed chip in there. You'll also use it for things like authenticating with APIs, with bearer tokens, passkeys, SSL, and etc. So cryptography. Let's quickly dive into how that works in computing. And specifically, we're talking about asymmetric cryptography here. So asymmetric keys are commonly used for both signing and encryption. Public key that we share, and a private key that we keep safe. So the private key is like a key. We can use it to access doors that we have the right to access. And a public key is like a padlock. I can share that with someone, and they can't open it unless they have the key to it. And so it's based on this kind of concept where the private key can be used to derive a public key, and that's quite easy to do if you have the private key. But going in the reverse is really hard. You can't easily compute the private key with the public key. And so you can share around your public key, and no one can really do anything that's that useful with it. So here you go. This is one of mine. Knock yourselves out. So if I give you a public key, you can encrypt a super secret message to me, and the private key does the reverse. So if you encrypt that message and send it to me, only I can decrypt that data. And signing, which is the concept really behind digital identity, works the opposite way. So if I sign some data and send that to you, you can use my public key to verify that I'm the source of that data, and that can only have come from me if the message matches the private key, the public key. And so only I can sign data with my private key, and anyone can verify that signature with my public key. We really generally use a hash of the data rather than the data itself, but I've simplified it a little bit for this example. So going back to our concepts of identity, an issuer can provide me with a signed credential, and I can share that with a verifier. And the verifier can verify that that signature matches the issuer's public key. And so even though I've had control of that credential, they can make sure that it's actually come from the source that they think it has, rather than from somewhere else. And I can't have tampered it in the middle because I don't have access to the private key from the issuer. And the key thing here really for privacy is that the verifier can do this without the issuer knowing anything about it, because that public key is public, they share it publicly, and so the verifier can verify my identity anywhere they want, and the issuer doesn't need to know about it, just as they wouldn't if I shared my passport at the airport. So, how do we issue a credential to a user? Here's the OpenID for Verifier Credential Issuance spec. It's actually a specification built on top of the OAuth 2 specification, which is commonly used for login. So you might never have seen it displayed like this, but I bet most of your apps in the room use this industry spec. It's how our apps interface with the outside world. And so I, as a user of an app, want to use my app to access some server on some data on a server somewhere. And so that resource server generally delegates the trust of authorization to a different server. And I can log into that different server. They will provide me with an authentication code and an access token, which I can then use to call that API. With verified credential issuance, the holder is just the client app, and the issuer is just the resource server. It's just the same as any API that we would normally call. So let's do a very quick demo. So this is the EU Digital Identity Wallet Reference implementation. You can just freely download this on GitHub. It's all open source. So what I'm going to do here is, here's a stub which I can go in and say I want a mobile driving license. Ooh, hang on. I want the other flow, pre-authorization flow. Cool. And I can just type in whatever I want to do to this, because it's just for testing. And so what will happen is, once we've got the data set up, we can be on any website here, and we should get a QR code. And so on the app, we can just open it and say, I want to add a new document to my wallet. I will scan the QR code. And then we'll type in the transaction code that it gives me as well on the screen. And there we go. That's the data all that you can see that I put on the website there. So we now have a new mobile driving license in the wallet. It's that simple. Cool. And this specification works regardless of the format of the credential. So as app developers, you're probably very familiar with JSON. JSON can be made into a JSON web token, which is commonly used as bearer tokens, but that's one of the main formats of credentials as well. And we can also use CBOR, which is the same format that's used behind passkeys. It's a slightly more efficient and concise mechanism for encoding data. So what about now, when I want to present my data? I have it in my wallet. What do I do now? So there's another standard called OpenID for verifiable presentations, which is also built on top of OAuth 2. But there's a second standard for presentation as well, which is the ISO-compliant mobile driving license. Cool. And so the ISO spec is actually what is behind the format which is used by Apple Wallet and Google Wallet as well. But since we're at an iOS conference, we probably care more about the Apple one. And we can just have a look at comparing these two specs. So the ISO one's really good for QR code and NFC and offline use cases. It's really optimized for mobile, whereas the OpenID verification kind of works for mobile, but a lot of it requires some internet access. The flexibility of the ISO one is more fixed. It requires the CBOR encoding rather than the JSON one, which is more flexible. Okay. And the adoption for the ISO stuff is much more specifically used for mobile driving licenses as opposed to any other kind of credential that you might want to use. So again, let's have a quick look at how this might work in practice. So we have a verifier. And let's say I want to see some attributes from a mobile driving license. We can select what attributes I'm interested in. So maybe I'm interested in the person's name and the fact that they're over 18. And then again, we'll get a QR code. And so I can go here. I can say I want to authenticate. And I'm going to do that online. This is a website after all. We can scan that QR code. And then it will ask me which of my two driving licenses that I might have in my wallet I want to use. And so let's say this one. And I'm going to say I'm over 18. Hang on, is that one over 18? This one's over 18. Let's go with that. So you want to share this data. You can share. And then we'll type in the PIN, which is the PIN for the wallet. You can obviously use Face ID for this as well. Let's say done. And now we can see the website's updated, and I've shared that data with the website as well. Cool. So this is great, but can we do better? Like, this is all online. It's sharing with QR codes, which isn't that helpful. And I've had to do stuff across devices, and I have to have the app open, which is quite annoying, right? Like, I'm used to going to a bar. I can tap the buttons on the side of my phone and get access to Apple Wallet really quickly. So there's this new thing called the Digital Credentials API, which is being pushed by both Apple and Google. It's actually built on top of the OpenID for verifiable presentations that we talked about before. And it's also being adopted kind of widely by Apple and Google in their first-party browsers. My hope is it's going to make it simpler to implement with a wider a range of wallets, particularly not other kind of third-party apps, not just the Apple Wallet. And as you can see, it's kind of merged into Safari into WebKit. But there's a feature flag for this in the Settings app. And I did try and get this working because I really wanted to do a demo. But here was what merged onto WebKit. And there's this thing that just says, the example is coming soon. So I had to play around, couldn't get it working, and kind of, yeah. So, but having said that, I still do have a demo. So if you'll forgive me, this demo is actually using Android. So Here we go. So if we go to Google Chrome, we can see the digital credentials demo. And so it's accessing for a particular set of information. We can say we want to request those credentials from the wallet. And then the browser is asking me if I want to share, if I trust this website to share my data with. And so now we can see what it's done is it's popped up actually a share sheet. And these are actually, it's kind of hard to tell, but you can see from the subtitle there that says wallet, and then the second one that says IC wallet. These are actually two different wallet apps. They're not the first-party wallet app that's Google Wallet or Samsung Wallet. These are just custom wallet apps that are built by third parties. And so it's now exposing that data to the browser so that they can choose which data I want to share. I get a warning here saying that the verifier that I'm using isn't in a trust list for the wallet that I'm using, but that's fine. We can trust it. It's only test data. Again, it asks me to enter my device PIN so that I can do this. We got an error. Oh, well. But there we go. It kind of, you can see how it's going to be much more interactive and much more built into the OS and to the browsers rather than having to share between different apps and have those apps open all the time. Cool. So we've seen how I can share data with a third party using these systems. And so now I've shared that data with you. You have access to it. And so how can we make sure that you can't then just reuse that credential to prove that you're me? Because now you have my data, you can prove that you're me, right? So to prevent reuse of that credential, we use something called holder binding. And this is something you're probably quite familiar with physical documents. Generally, it's something like biometrics, right? The driving license card or the ID card that I might have has a picture of me on it, and so you can use that to cross-reference that with my face and check that I am the rightful holder of that. We can also do something called claims-based. So the ID pass that I have for the conference doesn't have my face on it, but it does have my name on it. And my ID card has my name and face on it. So you can cross-reference that with an ID and make sure that it's the same. And we can also use cryptography, right? We've got this great thing that we can prove that the issuer is the right person. We can also use that in the same way with the holder. So we can add a cryptographic check and also to prevent it being moved from the device as well. So how does this work? Well, we have our holder. And the holder has a public set of public-private key pair as well. They can share that with the issuer, who can then issue a credential containing that public key. When the verifier comes along and wants to access some data, they can issue a challenge to the holder. And if that holder can share that credential alongside the signed version of that challenge with matching the public key in the credential, then they're the rightful holder of that credential. And then we can verify the issuer signature as well to make sure that all of the credential is fine. So, what about the private half of our key? This is tied to our identity as the holder, and we want to really make sure that it's kept safe. Right? We don't want anyone to get access to this. If it gets stolen along with my credential, you can then use it to steal my identity. So, many devices now have access to hardware-backed key storage. And this is true for any iPhone older than the iPhone 5S, iPad Air or later, and all Silicon Macs, all Apple Watches, and even the Apple TV. So, we can use that to store keys in Secure Enclave, and it supports hardware keys as well. And with hardware keys in Secure Enclave, credentials can be issued against these on-device keys. And since these keys cannot be removed from the device because they're in hardware-backed storage, there should be almost no risk that the credentials can be stolen. The almost is there because there are some really, really complex attacks that you can theoretically do but haven't been proven. Great. So no one can reuse my credential, but they do have access to my data. So this is already the case, right? When I share a physical identity document with someone, here's the example from a North Macedonia identity card, we can see that this contains my name, nationality, sex, signature, date of birth, place of birth, home, address, all sorts of information that the person that I'm giving it to does not necessarily need to know. Does the car hire place really need to know where I live? Does a nightclub bouncer need to know that over the age that I'm aged to drink? Do they need to know where I live? Do they need to know kind of my gender? Do they need to all of this other information? No. So we can share only the data that is required. And how do we do that? We use something called selective disclosure. And this is based on hashing functions. So a hash is a known and shared one-way function. It's deterministic, so it always produces the same output for the same input. It's irreversible. You can't kind of go back from the hash to the original data once you've done it. And it's lossy, so that kind of helps you kind of be able to match the same. Yeah. Anyway. But without the disclosure information, here you go, you can tell that my credential is valid, and you can use the proof key binding to verify me as the rightful owner, but you can't see the data that's not disclosed. It's all hashed, and you can just kind of see X, G, SL, I don't know what that means. But if I share the disclosures with you, the specific disclosures for the specific information that I want to share, along with a salt, just to make sure that we mix the data up a little bit, because the search space for things like dates is much more limited than you'd expect. And so then you can access that data, and you can verify the data in the credential by using the same hash function that we've used to hash it in the first place. Cool. So all of that's good. But what if you accidentally issue a credential, and then you want to take it back later? How do we do something like that? We have decentralized credentials. They're signed at the point of issue, and they're immutable because the signature is based on a hash of the content. If we change the content, the signature no longer matches. And so how can this in this decentralized system, how can we know when a status has changed? And we want to do this in a way that also preserves the user's privacy. The issuer shouldn't need to know when and where the user is using their ID. But we could linking to any URL that the issuer checks against could result in just this. So there's another specification for a status list. And issuers can provide a link to the verifiers to check the status of a credential in a way that's privacy-focused, cacheable for offline use. So we can have a long list of of bits in a file. And each credential refers to a single bit in this string. And so as long as we have a long enough list of credentials, the issuer doesn't know which of those credentials we're interested in. So in my credential, I can just have something like this, which is an index, and the index refers to one of those bits. And if it's 1, the credential is revoked. If it's 0, the credential is fine. And because a lot of the data is going to be the same, it's just 1s and 0s, and we kind of expect that most of the credentials are fine and not revoked, it's really good for compressing the data. And so for something like 100,000 credentials, it can take up just 16 kilobytes on disk. And actually, when compressed, it can be as little as 500 bytes. So it makes it really great for caching data and for downloading over the internet as you need. A few weeks ago as well, Google announced that UK citizens will also be able to use their passport to create a digital ID stored in Google Wallet. In this situation, Google issues a brand new credential based on data it's verified from a passport. This is a new credential, so that chain of trust from the original verifier is lost, which means that if the original document is updated, revoked, stolen, or lost, then the new derived credential is not. And the ID of our credential can't be checked against the original status list. But the way it works is something like this. The Passport Office issues me with my passport. I can present that to Google Wallet, who verifies that with the Passport Office. And then Google Wallet can issue me with a new credential that I can present to someone like National Rail to prove that I'm in a certain age to get a rail card, and they will verify that with the Google Wallet. This is kind of a great way of kind of having multiple credentials being available that aren't necessarily linked back to the government data that they need to be. Cool. So to summarize all of the stuff that we've been through, we've talked about the concepts behind digital identity. There's 3 main parties and a circle of trust between those parties. We talked about how we can sign data, and we can keep the private keys in the secure enclave to make sure that no one can steal our credentials or our identity. It's all based on some widely used industry specs, based on OAuth 2, which is kind of commonly used and trusted well within our industry. And we also have cryptographic holder binding and selective disclosure to make sure that all of our data is private, and we have control of who we share that with. Here's a list to all the specs again, if you want to read more. I also recommend Richard Pope's book, Platformland, if you're interested in how this plays within the public sector in particular. Chapters 4 to 6 are really good on digital identity. And the EU reference implementation for Digital Wallet, which we kind of demoed a little bit today, is also worth a look. The slides, links to all the specs, and everything else is in this GitHub repo here, if anyone wants to scan that, but I'll share them in Slack as well. Great. I'm Oliver. Hopefully I've proved that, but I'm happy to take questions if we have time. But yeah.
Thank you.